one more normal equation example. Again, Westley is involved. So our man in black, no one knows why this is happening. But anyway, so our man in black is this. The Dread Pirate Rabbits, erstwhile. Okay, 1, 3, minus 2, minus 6. As we've seen, it is a variable little beast because it has a one-dimensional column space, one-dimensional null space, one-dimensional row space, one-dimensional left null space, and it's 2 by 2, so we can draw pictures and understand things. So we're going to do one example where we solve for ax equals b, where b is not in, so let's blow this up, where b is not in the column space of A. So that's our important piece here, 5, 5. You can see that, right? So the column space has to be a multiple of 1, 3. So this is not good. Some part of this vector lives in left null space. Some part of it will live in column space. It's not completely in left null space. I think you can see that. But let's figure it out. So we go through the general solution problem, right? So you're asked to solve it. You line it up. This is the augmented matrix, right? So we've got the augmented matrix here. We do one step of row reduction, blah, 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 and we've got 0 equals minus 10. Right, so this is eq. No solution, right? It's inconceivable. And we understand what that word means. So then it is time for the normal equation, and that is this beastie here. So we simply take our A, pre-multiply by A transpose, and we pre-multiply the B by A transpose as well, and we set up this new equation. So that's what I've done here, right? So 1, 3, 1, 3, there's a 10. 1, 3, minus 2, minus 6, that's the minus 20. And that actually happens here again. That's the same thing, but the vectors are switched. So symmetry, and the last one is a 40. So let me make that clear. So this is A transpose A is always symmetric. I cannot say that enough. You should be absolutely all over the little proof, right? Very simple. A transpose B, similar business. 1, 3, 3, 5, which amounts to 4 times 5, 20, 20. This is really minus 8 times 5 because they're both 5s, so we get minus 40. All right, so now we just set up the new equation, right? So we take these two, put them into an augmented matrix situation. Our friend, the row operation, we're using the same thing. So there's a minus 20 over 10. We're just good people. We always do it this way. And now we've got zeros along the bottom. As all good, as promised. Right. We have not let ourselves astray. We have to get it to complete reduced row echelon form, so that's dividing through by 10 here. Let me get this to be bigger again. Right, so we're going to take this divide through by 10 here. Nice, nice, nice. So we get 1 minus 2, 2. All right, so that's it. Usual game. We have a pivot column and a free column. We express the pivots in terms of the free. Boom. Right, we just write out the equation and then express the pivots in terms of the free variables. There's only one of each, so we end up with one equation. This is our general solution story. So we always write this out. There's a star because this is an approximation, so I'm going to carry that around everywhere. So the first entry and the second entry, this is the free variable, and this is the pivot variable. So we replace the pivot variable in terms of the free. We leave the free variable as is. I put a 0 in here because might as well. And then we spread things apart. usual business, right? So here's the free variable multiplied by a vector. This will be the null space vector. And then this is a particular solution, right? So that's what we call a homogeneous solution and a particular solution. A homogeneous solution is always a null space vector. Particular vector, as we'll see just here, is more often than not a combination of a vector that lives in row space, which is kind of the best particular solution, and some null space vectors. So let me see if I can talk you through that. Talk my way through it, at least. Okay, so, and this free variable can be any number, right? Okay, good. So let's look at some things. So we can find the vector that we've actually reached. It's a times x star, because that's right, x star is our best solution. And so if we put this whole thing in, right, we take all of x star, dump it all in here, and solve it, and multiply through by a. That's here and here. So a is here and here. We're multiplying this first part here, and the second part is here. Now, of course, that second part has to be 0, right? This has to be 0, because has to go to 0, the 0 vector, because it's the null space vector, or the homogeneous vector. It satisfies a x star equals 0. So the particular solution does the work. Right, the particular solution does the work, and it gives us 2, 6. So 2, 6 turns out to be the best thing we can do. So let's see how that works. So nice big picture here. Okay, so there's a lot going on here. Now, we figured out this big picture for Westley before, so let's look at it again. This is our solution, 2, 0. Let's go back here, right? It's 2, 0. A times 2, 0 sends us to 2, 6, which is in the column space of A. The column space of A is any multiple of 1, 3, 3. Again, something worked out before, but you can just look at, it's a very simple matrix, so you can see that that's true. Okay. We're trying to get to 5, 5, but we can't get there, right? It doesn't live in the column space of A. So the difference is here, the 3 minus 1. So if we add these two together, 2 plus 3 is 5, minus 1 plus 6 is 5 as well, so that's good. And these things, if you look at these two, they're at right angles, right? So 2 times 3 plus 6 times minus 1, they are at right angles. If I've written that down. They have to be, right? P is perpendicular to E, right? This is in column space, P is in column space, E is in left null space. Have to be at right angles, guaranteed. So this is the best we can do. We're trying to get to here. The best we can do is here. If we were here, that's further away, right? We can only be in column space. So this is the best we can do. I wish I wouldn't do that. Right? Best we can do. So the piece that is missing is a pure left null space vector. Okay. Now, we can add any null space vector we want, and the null space is here, because that just gets sent to 0. So taking this particular solution and adding any null space vector moves us along this line of points, right? The origin is here, but we're going to take our particular solution and add a null space vector. Anyone, right? There's infinitely many. It turns out this is sort of the kind of best particular solution. It's in row space. It's an XR. XR is the best particular solution because it doesn't contain any null space vectors. It's right angles to, right? It's orthogonal to, I guess I don't need to put that, orthogonal to X n. It's kind of a big deal. So all of these gray, this is what this is saying, xp could be any vector along this line here, any vector. I'm going to leave that color there, maybe. Any vector along this line. By which I mean these vectors, boom, 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 all these gray ones. All of those get sent. They get sent to the same P. They get sent to this P. It's a bit of a subtle thing. Well, I mean, hopefully you can see it. So that's what I'm saying here is that xp is not equal to xr in general. It contains some of it, of a row vector, and it contains some of the null space vector. And here it is. It's a special particular that lives in A's row space. Very good. I like that. And this is just to show you that you can construct these examples, back the other way, right? So it was kind of easy to make this example. So we took a column vector and a left null space vector, multiplied them by some simple numbers, added them together to get a vector for which then we could solve, right? So we go back and we solve everything. Yeah. Right. So I think that is the plan. Yep. That's an extra bit, but it's useful to, in what we're thinking we're going to be solving Ax equals B, but it's okay to kind of build concoct an example because it helps you think about it in other ways. All right, so this is a great example to understand. It's 2 by 2. Pictures aren't too complicated, right? So we're not in 53 dimensions or even 3, but you can see hopefully how the normal equation is working here in great detail, right? So there's the sort of the algebra of the whole thing, and then there's this powerful geometric picture. So good, onwards.